In this video, we will discuss entropy. We shall give its definition, and we shall see how it is used to define second law of thermodynamics. We will present some simple calculations and solved problems to show how entropy change can be computed. Entropy is usually represented by the letter capital S. The SI unit to quantify entropy is joules per Kelvin. Now, this will become clear soon. And by definition, entropy is a quantitative measure of a disorder of a system in any specific state. And because the entropy is a measure of the disorder of a system in any specific state, it must depend only on the current state of the system. So let's assume a system that is presently in state I, or the initial state, and finally taken to a state F, the final state. When the system is in its initial state, the entropy of the system is S sub I, let's say, and when the system made its transition to the final state, the entropy is S sub F. So as the system proceeds from its initial state to the final state, the change in the entropy of the system is defined as the final entropy minus the initial entropy. Now, because entropy is a state property, or sometimes it's known as function of state, the difference in entropy between the final state and the initial state must depend only on those states and not at all on the way the system went from one state to the other. In other words, it's independent of this path. So the mathematical formula to compute the change in entropy is quite simply given by the following expression: IF dq over T. T is the temperature of the system in the unit of Kelvin. Q is the heat transferred to or from the system, and the integral runs from the initial to the final state. We will see later how to use this expression to compute the change of entropy for some cases, but next an important point. In order to compute the change in entropy using this equation, the process through which the system evolves as it goes from initial to the final state must be a reversible process. So the question is, how do we compute the change in entropy if the system starts from the same initial state and evolves to the same final state, however following an irreversible process, such as the one shown in green? However, because of the fact that entropy is a function of only the state of a system, shows we can simply invent a path connecting the given initial and final state that does consist entirely of reversible processes and compute the total entropy change for that path. Although this is not the actual path, and the actual path is the green path, the entropy change for this path must be the same as the entropy change for that path, because entropy is a state property. So the change in entropy is dependent only on the initial and final point. So we can make use of this analytical equation to compute the change in entropy. An important point is that entropy of a closed system as a whole either remains constant or increases. So namely, we can write the following for the change in entropy of the system. The change in entropy can be greater than 0, namely when the entropy increases, or equals to 0 when the entropy remains constant, but it can never decrease. So this fact is one form of the second law of thermodynamics. Now we note here that the greater than sign applies to irreversible processes and equal sign to reversible processes. So an example is a reversible cyclic process. This is a pressure volume diagram. So let's say you have the initial point, the final point, and the system evolves in a following manner. It starts and ends up the same point. So this is a process that is cyclic and reversible, and for this process the change in entropy is identically zero. Here are examples of irreversible processes for which the change in entropy is positive. The first one is when ice at 0 degrees melts to water at 0 degrees, free expansion of gas at a constant temperature, and also heat transfer between two heat reservoirs. Now we shall see how to calculate the entropy change for these processes next. Let's say you want to calculate the change in entropy when 1 kg ice melts to water at 0 degrees Celsius. As we have seen before, the change in entropy is given by that equation, integral of dq over t. Now this process is happening at a constant temperature of 0 degrees Celsius, so you can take that temperature out. Now remember, T must be in the units of Kelvin, and integrate dQ. T in Kelvin is quite simply 273. 0 Celsius equals 273 Kelvin. The integral dQ is just the total heat. And from our previous video, we know that Q is quite simply mass times heat of fusion for water. Now the mass is 1 kg. That is 1. Heat of fusion for water is 3.35 times 10 to the power 5 joules per kg, which will give you 1,227 joules per Kelvin. So that is the change of entropy for this process. Now let's say we have free expansion of an ideal gas. You have 1 mole of an ideal gas expands isothermally to twice initial volume. So to calculate the change in entropy, of course we use that equation that we have seen before. Now we note that this is an isothermal process, so that means the change in internal energy is 0. So the heat added must be the same as the amount of work done. And we also know, since this is an ideal gas, from the ideal gas law, P equals 1 mole RT over V. Substituting all this information in this integral, we get the following. So dq is RT over V, and there is a t there, dV. So the t cancels, and you get R, which can be taken out. That's just a constant, dV over V. Now note the volume is increasing twice the original value. So if the original value is, let's say, V sub I, the final value is 2VI. So the result simply becomes R times natural log of 2VI over VI. The VI cancels, and the answer is R natural log of 2. We know R is a universal gas constant with a value of 8.314. Substituting that in here, you get 5.76 joules per Kelvin for the increase in entropy for the system upon free expansion. Let's look at a problem. 1 kg of water at 100 degrees Celsius is mixed with 1 kg of water at 0 degrees Celsius. If the final temperature of the system is 50 degrees Celsius, calculate the total change in entropy of the system. Assume the specific heat capacity of water is 4,190 joules per Kelvin per kg over this temperature range. So let's first calculate the change in entropy for the hot water as it cools down to 50 degrees Celsius. Let's denote that as delta S H, and that is given by dq over T, and it cools down. So initial temperature in Kelvin is 373, the final temperature in Kelvin is 323. 50 degrees Celsius is 323 Kelvin. Since this involves specific heat, then we have to use the equation that we have seen in one of our previous videos, and that is mc dt over T. M is 1 kg, C is a constant, 4,190, and putting everything together we have the following result, which can then be integrated to give you natural log of 323 over 373, which will give you minus 603 joules per Kelvin. Now this is only the contribution from the hot water. Now let's do the same for the cold water as it warms up to 50 degrees Celsius. So the change in the entropy of the cold water is quite simply given by the similar equation. The mass is 1, specific heat capacity for water is 4190. Now the initial temperature was 0 degrees Celsius, in Kelvin 273 Kelvin. Final temperature is 50 degrees Celsius or 323 Kelvin, dt over T, which can then be computed to give you a value of 705 joules per Kelvin. The total change in entropy of the system is just the sum of the two values that we have computed, and that's going to give you, when you sum 705 to minus 603, you will get positive 102 joules per Kelvin. As you can see, the change of entropy is positive, or entropy actually increases during this process. Problem 2, heat transfer. A cylindrical copper rod, so that's this one right here. Length is 1 meter, radius is 3 cm. It's insulated to prevent heat loss through the curved surface. One end is attached to a thermal reservoir at 200 degrees Celsius, so that is this one right there, hot reservoir. And the other one is attached to a reservoir at 20 degrees Celsius, a cold reservoir. Find the rate at which entropy increases for the rod reservoir system. The thermal conductivity of copper is 401. Since in this case you are calculating the rate of entropy increase, not just the increase in entropy, we have to use the rate of heat transfer here and there. From our discussion on heat transfer, the rate of heat transfer is quite simply the conductivity times the cross-sectional area of this cylinder over length times the temperature difference, in this case 200 minus 20, which is 180 degrees Celsius or 180 Kelvin. Heat is flowing out of the hot reservoir, so the rate of change of entropy there is quite simply 1 over 200. Convert that into Kelvin, 273, times this entire thing, which is Ka over L times 180. And that's going to give you, note, K is 401, L is 1 meter, and A is pi 0.03 squared. It's a circular cross-sectional area. Since heat is leaving, so that's a minus, and it's going to be minus 0.4315 joules per Kelvin per second. Likewise, for the cold reservoir, the change of its entropy, the rate of change of its entropy is positive because heat is flowing into that cold reservoir. Note the temperature in Kelvin is 20 plus 273, the same Q over T, and that will give you that, plus 0.6965 joules per Kelvin per second. Adding the two numbers will give you 0.265 joules per Kelvin per second for the rate of entropy increase for the whole system.